If you look in that document, okay, the beginning section, you see just basically your definition of the derivative, and these are all derivatives that you know, that first page there, okay? And then these are some additional derivative rules. This packet, you need to keep this packet with you at all times, okay? When we do some of the practice AP exams, I'll let you use this packet for the first couple, but then you have to kind of wean yourself off of it. The inverse function, this is one that I told you we are not going to spend time on, okay? So this is one that you will see on your AP exam. We'll just practice actually using it then, okay? How could there possibly be a question? What? Okay. Average rate of change, you know this, you know this. You know basically this whole first section here, okay? You know this. These are our basic definitions. You know all those. You know your differentiation rules. We've done all that. Okay. And we've talked about the intermediate value theorem. Now, there are several theorems. We're going to start talking about some more today. There are several theorems that you have to be familiar with to the point where they're not going to specifically say intermediate value theorem or mean value theorem, or they may not even specifically say that you need to look at the definition of continuity. But the questions, in order to answer the questions, you have to know those specifics. Like if you have a question about continuity, you have to know those three things that we look for with continuity. Do you remember what they were? In order for something to be continuous, right? F of C has to exist, right? The limit as x approaches C of f of x has to exist, which means the limit from the left is equal to the limit from the right, right? And then the third part was that the limit as x approaches C of f of x is actually equal to f of C. So when you're talking about continuity, you have to use these three things to prove that something is continuous. Okay, when we talk about the intermediate value theorem, okay, you should write this in your little note packet, right? The intermediate value theorem, what do we typically use that to show? We typically use that to show that a y value does fall between the two y values that we have. That's what the intermediate value theorem is saying, okay? So if you look at this, function f of x is continuous on AB, right? So it's continuous. If it's continuous, what do we know? We know these things. It exists at that point, the limit exists, and that the limit is equal to the function at that point. Y is between f of A and f of B. So if you look at this diagram here, I don't know why they used D instead of Y, but right, Y is between f of A and f of B. Then there exists at least one number C on the open interval, right? So there has to be a number C on the open interval such that f of C, well, that's a really bad example. Let me use, here, I have it here. That was dumb. Here's your C. F of C falls on that interval, okay? So basically, right, this is important. The intermediate value theorem is usually used to show that the function crosses the x-axis. So usually what we end up doing is we end up using this to show, so if you have a function that's doing something like this, right? And let's say that this is your f of B and this is your f of A. Well, according to the intermediate value theorem, there must be some point between A and B where it crosses the x-axis or where it's equal to 0. Okay? So this is important to recognize. The intermediate value theorem says that if I have an f of A and an f of B, right? And if f of C is between those two, then that means C is between A and B. Okay, let me say it again because I'm not sure, based on the faces that I'm seeing, I'm not sure that you're all getting this. And this is pretty important. Okay, the intermediate value theorem, I don't like the graph that they have drawn there, but the intermediate value theorem is saying, let's see here, let's just go something like this, right? And we'll call this A, and this is B. So that makes this point right here, this is f of A, and this point right here is f of B. Okay? What the intermediate value theorem says is that if I have a y value between f of A and f of B, if I have a y value somewhere in here, the intermediate value theorem says there must be an x value between the A and the B that corresponds to the y value between there. We typically use this to show that we have a 0 between the A and B. We use it to show that we have a 0 that occurs on that interval, on that open interval, AB. Why do we do that? Because if I know that there's a 0 that occurs between A and B in the derivative, let's say that this was f prime, right? F prime of x, then I know that this curve is changing from, f prime of x is changing from negative to positive, which means I know it's changing from decreasing to increasing. This 0 on the f prime curve tells me there must be a minimum, a relative minimum on f of x that all connects. I know, right? If I'm given an f prime of x that is continuous, I can use the intermediate value theorem to basically prove that there's a relative minimum. Okay, so these are the types of things. The intermediate value theorem is what we use to prove that the value exists on that open interval, such that the y value is in between f of A and f of B. Okay, that's our intermediate value theorem. The next one that I want to talk about is the mean value theorem. The mean value theorem basically says, this is really an easy one, if f of x is continuous and the first derivative exists, then there is at least one number on that open interval such that this is true. What does this mean? What does f prime of C mean? The slope, which is the instantaneous rate of change. What does the other side of this equal sign stand for? The average rate of change. The mean value theorem says that if I have a continuous function and the first derivative exists, so in other words, it's not something like this, right? If I have a continuous function and the first derivative exists, that somewhere on that interval, the instantaneous rate of change is equal to the average rate of change, right? If my average speed driving to 0 is 78 miles per hour, okay? The mean value theorem says that at some point in time, I had to have been driving 78 miles per hour. Right? If I only drive maybe a maximum of 77 miles per hour, then it is impossible for my average speed to be 78 miles per hour. In order for that average speed to be 78 miles per hour, at some point in time, between the time I left here and the time I got to Vero, I had to be going 78 miles per hour. At some point in time. Otherwise, it's just not possible. Now, if I'm driving 79 miles per hour, is it possible to have an average speed of 78 miles per hour? Sure. Yeah.
How do you have the first derivative exist on the integral part again?
How do we know when a derivative exists? Let me just rephrase that. How do I know when it doesn't exist?
It's when it's constant.
No, constant it can exist. If it's a corner or a cusp, right? Sharp point. If it's discontinuous.
Would they have to give you the graph then to see
No, you can recognize some just from what you know. You know, an absolute value function is not differentiable, right? A discontinuous function is not differentiable.
How does a cusp look like then when it from? No, I mean
that you'd have to look at the graph to know that. Right. Okay. So the mean value theorem says that if we have a continuous and differentiable function, at some point in time, the average rate of change is going to be equal to the instantaneous rate of change. That's the mean value theorem. Compared to the intermediate value theorem, which is basically finding that point between the two y values, right? So the intermediate value theorem says that if my y is falling between the two y values, then my x has to fall between the two x values. That's what my intermediate value theorem is saying. Okay? The mean value theorem says my average rate of change has to equal my instantaneous rate of change. Graphically speaking, that means that the slope of the secant line, my average rate of change, is going to be the same as the slope of the tangent line at some point. Okay, that's what it says graphically. Okay. Rolle's theorem. Okay, 3 theorems we're going to talk about today. And we'll talk about extreme value theorem later on this week. Rolle's theorem. I have a continuous and differentiable function. Now notice the 3 theorems we've talked about. 2 of them have to be continuous and differentiable. Of course, differentiable implies continuous, right? So if it's differentiable, we know it's continuous. Right? 2 of them say differentiable and continuous. 1 simply talks about continuity. So the intermediate value theorem, it just has to be continuous. It doesn't have to be differentiable. The mean value theorem is continuous and differentiable. Okay? All right, so the Rolle's theorem says if a function is continuous and differentiable and f of a equals f of b, then there's at least a c value on that interval such that f prime of c equals 0. So this is what this looks like graphically. Right. So here's a, here's b. All right, let's go like this. Okay, so here's f of a, and there's f of b, right? So here's an example of a continuous and differentiable function where f of a and f of b are equal. It says there must be a value c between a and b such that f prime of c equals 0. Can you see a point where that's true? Yeah. Okay, I love the way you just said that Because if that's the case, right, here's that C value where f prime of C equals 0, right? So basically what the Rolle's theorem is telling me is that if there's a point where f of A is equal to f of B, what must exist between A and B? A turning point, or we want to call it a maximum or a minimum, right? An extreme point, extrema. We call it relative extrema. Rolle's theorem is talking about relative extremas. Okay? Rolle's theorem says, hey, if I have an f of A and an f of B that are equal, somewhere in between it must have turned, which means somewhere in between I've got a relative minimum or relative maximum. And it's kind of disguised. You don't realize that that's what it's saying. It's got this complicated looking theorem. You're like, why can't they just say if the y values are equal, there must be a relative minimum or relative maximum? Because mathematicians like to sound like they're really complicated. Okay? But that's what that's saying. Because f prime of C equals 0, that means the slope of the tangent line is equal to 0. Okay? All right, let's jump over to our notes now. Okay, lesson 1, we're going to jump down here to the actual mean value theorem. Okay, let's see here. All right, just some things that are important to notice, right? If f is continuous on the closed interval AB, and where's my A? A is missing. Here's A right here. And differentiable, well, we can see it's continuous and differentiable on that interval. There exists a number C such that f prime of C, so this is the slope of the tangent line, f prime of C, is equal to the average rate of change, which is right here, f of B minus f of A over B minus A, right? This is our tangent line, and this is our secant line. Okay, I like this little summary down the bottom here. Verbally, the instantaneous rate of change equals the average rate of change on that interval. Graphically, the tangent line is parallel to the secant line. Okay. It's really cold in here right now, doesn't it?
It feels good.
Okay.
If anything, that's
Okay. Here's our Rolle's theorem. Again, notice the continuity. When we talk about continuity, we're talking about the closed interval. When we talk about differentiability, we're talking about an open interval. Okay. Okay, Rolle's theorem basically says that f of A equals f. If f of A equals f of B, then there's at least a point where f prime of C is equal to 0. Okay, so this is my tangent line, and this is my secant. Okay. Okay. So basically that means that there's at least one number between A and B such that the tangent line is horizontal. Okay. Which means that there is at least one point in there where there is a relative min or relative max. Okay. Okay. Let's look at this example 1 here. Okay, this is the type of question you might see on your AP exam. So we've got a table of values. Sketch the differentiable continuous function on the grid. Okay, so let's just make a little sketch of this. See, we've got 0, 1, 2, 4, 4, 8, 6, 12, 7, 13, 9, 11, 11, 8, 13, 6, 15, 8, and 17, 4. Okay, we don't have to be exact. Did I make a mistake?
17, 14.
Oh, thank you.
Get it right. Good job.
Okay. Okay. So the key here is we don't have to be exact, but we do want to recognize that this is not a point, right? It needs to be kind of like, I call it soft curves, right? Because it is differentiable and continuous, right? Okay. So that's how I'm gonna make my curve. And sometimes they're nice on the AP exam and they give you questions like this. And to me, these are like, they're just giving you a couple points. Okay. Okay. Find the average rate. Let me make sure I did what I was supposed to. Use a table of values to sketch the differentiable continuous function on the grid. Okay. Find the average rate of change of g of x on the interval 2, 9. Okay, make sure you label this, by the way. This is g of x. Average rate of change between 2 and 9. Okay, so we're looking here and then 9 here. Okay. I'm looking for the average rate of change right there. Okay. So average rate of change is, we're going to do AROC. That's going to be g of 9 minus g of 2 over 9 minus 2, which is 11 minus 4 over 7, which means my average rate of change is 1. And does that match up with our graph? If we look at the slope, sure enough, this has a slope of 1. So that does match with our slope, with our graph, okay? Everybody good so far? Is g prime of 6 equal to the slope of the secant line from part A? Okay, g prime of 6. So here's 6. So we're looking right here. G prime of 6. So that means we need to be looking at the slope of that tangent line. That's pretty rough, actually, but let's see. Let's see what we can do there. That's kind of a rough one to work with, isn't it? All right. Okay, so glancing at it, what do you think? No, but we have to prove it, right? So we're going to say no. Now, if you were just given the table, how would you determine what g prime of 6 is from the table? Can you do that?
Well, it's like like the slope. Can you do the slope? The equation between
Okay.
5 and...
Get as close as we can, the smallest interval possible. So we could do like from g of 7 minus g of 6, we could do something like that. But that's going to give us a 1. G of 6 minus g of 4. So yeah, looking at that, that's going to be pretty rough. 7 minus 4 is 3. 13 minus 8 is 5.
Take the derivative of a linear equation, then it would just be that number.
You like stopped mid-sentence. He says, so then you could.
She said, I don't know.
No, because I was like, if you find the slope, you know it's a linear equation. The slope area.
So if we can just find the slope of this line, is that what you're saying?
And then the derivative of a linear equation is just the number in front of the x, which would be your slope. And then if you know this.
You're right, but you're making it really complicated. Yeah, let's just find the slope of this line. Can we find the slope of this line? Let me see. I know this point, right? So I've got the point 612. Can I find another point? How about, where's the 4? 4 should be, all right, let's, trying to find a good point here. 8?
13. It's almost hitting like 14.
How about 7? 7's up here at the 14.
Oh, that's what I meant.
7, 14, something like that. Okay, let's use that. Okay, so let's do, we're going to just call slope of secant line. I'm sorry, so slope of tangent line. Sorry about that. Slope of tangent. So we're going to do f of 8 minus f of 6. And it's going to be 8 minus 6. So f of 8 we're saying is about, looks like 14. All right, so 14 minus 12 over 2, that equals 1. So we said no, but so this is a really good exercise, because this is the type of thing you're going to encounter on the AP exam. Because looking at the graph, we know that it's not. We know that it's not, right? But the points that we chose are not proving that it's not, is it?
You chose 7, 14, not 8, 14.
Oh, well, that'll make a big difference too, won't it? Wait, f of 7. Ah, there you go. Okay. But let me just finish with what I was saying. Because sometimes that will happen. Like if you look at just a little piece of it, it seems to actually prove it. And part of the problem is that we're kind of estimating this value here, and it's not a really good fit. So when that happens, pick 2 different numbers, because looking at it graphically, it is clearly not parallel, and they're not the same slope. So pick 2 different numbers so that you can prove what you're saying, right? Yes.
For B, are we still using the interval 2 and 9? Because that's what you use as your secant line, right? The 1. You're saying the slope of the secant is 1.
Okay, let me finish this one, and then I'll answer that question. This was f of 7, right? Which was 14. So this is 7 minus 1. So we got 2. So we can say 2 does not equal 1. Therefore, g prime of 6 does not equal the slope of the secant. Right. Okay, I'm sorry, Caitlin. Say that again.
Are we still working on the interval 2 to 9? Because that's where we found the secant line was 1.
Well, is g prime of 6 equal to the slope of the secant line from part A? So yes.
Oh, I didn't see the from part A.
Yeah. Yep. Everybody understand that? Okay. Does Rolle's theorem apply on the interval from 4 to 9? Explain why or why not. What does Rolle's theorem tell us? Oh, okay. Well, not just maximum. Okay, so the interval from 4 to 9, was it? 4 and then 9. Okay. Rolle's theorem says that if f of A equals f of B, okay, is there a point on this interval where f of A equals f of B? Let me get rid of some of this extra stuff here. Is there a point on this interval where f of A is equal to f of B? Sure. Well, yeah, we could just say, okay, right here and right here, right?
You could also do 5 and 9.
Yeah, so that clearly is the case, right? Let's see. Does Rolle's theorem apply on the interval from 4 to 9? On the interval from 4 to 9, does the Rolle's theorem apply? Let's just double check our definition, right? Continuous on the closed interval AB. Okay, so it is continuous on 4 to 9. Differentiable on the open interval from A to B. Okay, it is. Okay, so let's apply the actual definition, right? It is continuous on 4 to 9. It is continuous. It is differentiable. It is differentiable from 4 to 9. Okay. Now look at the definition. Right? If f of A equals f of B. Now in this question, what is A and B? 4 and 9. Does f of 4, or g of 4, equal g of 9? No. G of 4 equals what? G of 4 is 8. G of 9 is 11. Right? 8 does not equal 11. Therefore, right, look at the Rolle's theorem. And I'll go back and talk more about it in a second. Right? Rolle's theorem. Exists a value where the derivative is equal to 0 on that interval. Okay? So in other words, this means that g of 9 minus g of 4 over 9 minus 4 does not equal 0. Okay? Now, here's the tricky part. Because understanding Rolle's theorem, there is a point, there is an A and B between these 2 points where Rolle's theorem would apply. Right? There is an A and a B between those 2 points where Rolle's theorem would apply. Do you agree with that? Okay. Now, the interpretation of the question is sometimes a little bit confusing because if you don't interpret this as being purely from 4 to 9 and f of 4 and f of 9, then you could answer this incorrectly. That's where we have to be careful to actually read the theorem. Okay, so if you look at this theorem, it's the endpoints that we're looking at. When you're given an interval, it's the endpoints there that we're actually looking at. So according to Rolle's theorem, this f of 4 has to be the same as f of 9. It would have, that curve would have to be coming down somewhere like that instead. Okay, everybody understand that? Okay. All right, the next question, we already answered that. Is there another interval where Rolle's theorem applies? Yes, we could make the interval, the best way to do it, use the table, right? Use the table right here.
Like 4 to 11.
4 to 11, right. Yes, oops. All right, I'm going to say 4 to 11. Okay.
Could 10 and 15 be another one?
4 and 15 or 11 and 15, right? It's got to have the same y value. So we could have used that one also. Has to have the same y value. Okay. So we're going to say g of 4 is equal to g of 11. Right? It's continuous and differentiable, right? It tells us that. Yep. It's continuous and differentiable, right? Continuous and differentiable. Okay. And let's see, looking at the slope. Okay. So the slope is going to be g of 11 minus g of 4 over 11 minus 4. So that's going to be 0 over 7, which is 0. Okay. Okay, so when we're justifying Rolle's theorem, we have to show that it's continuous and differentiable, and in this case, they told us that, so we didn't have to prove anything, right? And then we have to show that the slope of that secant line is 0. Yeah.
On the ones where you have to prove that it's like differentiable and continuous, can't you just? Oh, I guess isn't the first rule of differentiability that it is continuous?
Yes.
I was gonna say, couldn't you just prove that it's differentiable, but then that's still doing both?
Right. Okay. Let's scroll down to number 4. You're going to see more mean value on your exam than you will Rolle's theorem. Okay. So here we have h of x equals 5 minus 4 over x. Find all values of c in the open interval from 1 to 4. Okay. From 1 to 4. Guaranteed by the mean value theorem. Tell me again what the mean value theorem says. Right. There's some place in between or between this on this interval, the instantaneous rate of change will be equal to the average rate of change. There's got to be some place in there. Okay. So in order to find the instantaneous rate of change, what do I do? Take the derivative. Okay. H prime of x equals, right? So this is going to be 5 minus 4x to the negative 1, right? So that's going to be a positive 4 x to the negative 2. So that's 4 over x squared. Okay. There's my instantaneous rate of change. Right. My average rate of change, what am I going to do for that? Slope. Okay. So h of 4 minus h of 1 over 4 minus 1. Okay. H of 4, that looks like it's 4. H of 1 is 1. Bless you. So that's 1. That's my average rate of change. Okay. Find all values of C on that open interval. So IROC equals AROC. Find all values of C. I have an actual number for the average rate of change. The average rate of change on that interval is 1. So what do I need to do? I have to find where the instantaneous rate of change is also 1. So we're going to do 4 over x squared equals 1. Figure out which x values will give me 4 over x squared equals 1. So 4 equals x squared. So that means x is plus or minus 2. But of course, negative 2 is not on that interval. So x equals 2. Right? That is the point on the interval from 1 to 4 guaranteed by the mean value theorem. So at x equals 2, okay, Here's my average rate of change here on the interval from 1 to 4. There's my average rate of change. And here's my instantaneous rate of change at x equals 2. Oops. They sure look parallel to me, which means their slopes are the same. Okay. Does that make sense? Okay. Just going to talk through example 3 with you. We're not going to actually do it. Okay. A sports car speedometer registers 50 miles per hour as it passes a patrol car stationed at a mile marker. 4 minutes later, the car passes another patrolman at a marker that is 5 miles from the first car. The driver notes that the speedometer registers 55 miles per hour. Can the highway patrol use the mean value theorem to prove that the driver was exceeding the speed limit of 70 miles per hour at some time between the 2 mile markers? At 1 mile marker, he was going 50 miles an hour. At another mile marker, he was going 55 miles an hour. Can we prove that he was going 70 miles an hour?
Yeah.
How?
The time between.
The time between, exactly. Yes.
Yeah.
Okay.
That's the one where if they equal it, then that means it's a math. That's the one where the average rate of change equals instantaneous.
Yes, that's the mean value theorem, right? Okay. And that is basically how your radar detectors are programmed. Okay. Okay. Mean value theorem. Okay, can identify where the graphs rise or fall. The functions with positive derivatives are increasing and the functions with negative derivatives are decreasing. We've talked about this before. Find all values between the x values for which Rolle's theorem holds. Okay, I don't want to do any more Rolle's theorem. Let me see. I'm going to go down to the next one, mean value theorem. Determine whether g of x equals sine 2x plus 2x satisfies a hypothesis of the mean value theorem on the interval from 0 to pi. If so, find all numbers such that, okay. So if you look at this, right, this is where you have to be aware. We're beyond that point now where your teacher's just telling you what steps to do and what letters to write and what numbers to write. We're beyond that point. You've got to recognize it and think it through. What is this equation? Look at this equation. What is this? G of B minus G of A. If I had B minus A over here instead of on the right side, now tell me what that means. That's your mean value theorem. This is my average rate of change. This is my instantaneous rate of change, right? So we should recognize that. Okay. So that means, first off, let's figure out what that g of pi minus g of 0 over pi. So g of pi, that's going to be the sine of 2 pi plus 2 pi over pi. All right, what's the sine of 2 pi? Zero. All right, so that means the average rate of change on that interval is 2. The average rate of change on that interval is 2. Okay, now let's take the derivative. G prime of x. All right, taking the derivative of this. What's the derivative of sine 2x? Cosine 2x times 2. Good. plus the derivative of 2x, which is 2. So g prime of x equals 2 cosine 2x plus 2. Okay. Now my mean value theorem, right? We're going to do g prime of x equals g of b minus g of a, right? Divided by b minus a, right? Mean value theorem. We want to make sure that we're stating that. So that means g prime of x times b minus a equals g of b minus g of a. Okay. Okay. So g prime of x, that's right here. So that's 2 cosine 2x plus 2 times b minus a. What's b minus a going to be? Pi minus 0 equals g of b, which we said was g of pi at 0, minus g of a, g of 0, which is, what did I do there? That's so distracting. I have lost track of what I'm doing.
They're doing a thing where it's like a simulation on the board, and then you have to like jump over it or like duck.
Seems like a lot of.
Miss Lori, why don't you just set the 2 cosine 2x?
Yeah, why don't I just do that? Because I'm distracted. Holy smokes.
Why did you time?
Oh, yeah, hold on. Let me back up.
Use the original equation, which is the same as the one.
Let me just back up. Sorry.
There's other classes going on.
I don't know if that's an AP class.
That's just what I was going to say.
Okay.
But also we're
All right, let me see. G prime of x. So that's 2 cosine 2x plus 2 equals this. So equals 2. There you go. Okay. All right, so we have 2 cosine 2x plus 1 equals 2.
Why can't you just stop and say they don't equal each other since it's not?
No, we have to find the x value where they do equal each other. We have to find the x value where they do equal each other.
So for all of this, you're just solving for x.
Right. Okay, so let me back up because we got distracted, or I got distracted, right? So the mean value theorem means that I have to find that x value that's on this interval, right? I have to find the x value on this interval where the average is equal to the derivative or equal to the instantaneous. So first I found the average on that interval. That's my average. I have to find the x value where that average is equal to this, because that's the instantaneous. Okay? So that's what we're doing now. So let's see. So I'm going to divide by 2. So that's cosine 2x plus 1 equals 1. Subtracting 1, so cosine 2x equals 0. Okay, so where is the cosine equal to 0? 90 and 270, okay? So that means right here, 2x is equal to 90, or 2x is equal to 270. So x is equal to 45, or x is equal to 135. Okay, now let's put these in terms of pi, because the interval is 0 to pi. So x is equal to pi over 4, or x is equal to 135, which is right here. let's see, pi over 6, 3 pi over 6, 4, 5, right? Did I do that right? Pi over 4, 3 pi over 4. Those are the two places. Okay? So if we were to look at the graph of sine 2x plus 2x, which we'll do in a moment once you guys finish, bell's going to ring on us, isn't it?
Yeah.
Sine 2x plus 2x. Okay. Window going from 0 to pi. Okay. And we'll go -3 to 3. Okay.
Solving for x.
Say it again?
So you're basically solving for x.
Yes, we're solving for x. Yeah. 0 to pi.
Yeah.
Okay. So there's two places on this interval where the average rate of change will be equal to the instantaneous rate of change, right? One will be at pi over 4 and one will be at 3 pi over 4. Okay? Okay, homework. I'd like you to do numbers 1 to 10 on your homework 5.1, which is in your Google Classroom. Okay. Bye-bye. Thank you. See you Wednesday.